I welcome all of you to the class, and today is our lecture 1. So today we are starting with lecture 1, and today's lecture is about solving. Today we'll be discussing the concept of solving nonlinear equations, solving nonlinear equations. Solving nonlinear equations. Okay. Now, as far as the nonlinear equations are concerned, we know that the equation that we often use, that we are familiar with as an equation y as a function of x is equal to mx plus c. We're quite familiar with this equation, and we know we often call this as an equation of a straight line. This is an equation of straight line. Okay. We often say that this equation is a linear equation. The reason for calling this equation as a linear equation is the power of independent variable is the power of independent variable that is x. Okay, when we say y is a function of x, that means we often call this as x as an independent variable. We call x as an independent variable, and y we call as the dependent variable. We call y as the dependent variable. Okay, now if the equation between x and y is of the form y is equal to mx plus c, if the equation between y and x is of the form mx plus c, then we say that this equation is the equation of a straight line, and we say that this equation is a linear equation. The reason is this equation is having x raised to power 1. Okay, so when you write x raised to power 1, you call this equation as a linear equation. Okay, now if the equation happens to be of power other than 1, if you have an equation in the form of if you have equation y is equal a naught plus a1x plus a2x square plus a3x cube, we say that this equation is a nonlinear equation. This is not a linear equation. This is a nonlinear equation. The reason is the maximum power to the x, the maximum power to the independent variable is 3. Okay, the maximum power to the independent variable is 3, and it's not equal to 1. It's not equal to 1. When the maximum power to which an independent variable is raised to power is 1, we call the equation as linear equation. When you have equation raised to power 2, raised to power 3, or any other natural number, okay, or any other real number, we should say a real number, okay, or raised to power any real number, we call that equation as a nonlinear equation. That equation is called a nonlinear equation. For example, we have y is equal 3x raised to power 1 by 2. This is x raised to power 1 by 2. This is also the nonlinear equation. Okay, so when we classify the equations as linear and nonlinear, we can simply say that in case of linear equations, we have y as a function of x, y is a function of x, and the power to x is equal to 1. Okay, and if you have a nonlinear equation, again y is a function of x such that x is raised to power any real number. X is raised to power any real number except 1. except 1. Okay, so if you have y as a function of x, x is raised to power 1, you call that as a linear function. If you have x raised to power any real number other than 1, you call that as a nonlinear equation. Now, today we are going to study how do we solve the nonlinear equations. Okay, for example, if I take an example of an equation y as a function of x and a nonlinear equation, let me write as, let me ask you that we are supposed to solve the equation that we have in hand, the first equation. We have to solve y is equal x cube minus x minus 4 equal to 0. This is a nonlinear equation. First of all, we can classify this equation to be a nonlinear equation. The reason for this equation to be a nonlinear equation is the power of x. The power of the independent variable is other than 1. We call this equation as a nonlinear equation. Now we are asked to solve this equation. When we are asked to solve this equation, what do you mean by solving the equation? Solving the equation means find the values of x, find the values of x, find the values of x at which equation, let me call this as equation 1, at which equation 1 is satisfied, at which equation 1 is satisfied. It means give the values, find the values of x, which you substitute in the equation 1 will make left hand side of the equation equal to 0. Okay, we know this is a cubic equation. For a cubic equation, the number or finding the values of x, we also call the values of x as the roots of equation. We also call them as the roots of equation. That is, we have to find the roots of equation 1. Find the roots of equation 1. Since equation 1 is cubic, since equation 1 is cubic, therefore number of roots it will have, therefore number of roots it will have, therefore number of roots it will have will be equal 3. Okay, if we have a quadratic equation, we know like nonlinear quadratic equation like x square plus 4x minus 3 equal to 0. This is a nonlinear quadratic equation. Okay, quadratic equation is a nonlinear equation because the maximum degree of the independent variable is 2 other than 1. Okay, and we know the roots of a quadratic equation, its power is 2. Okay, therefore it will have two roots. We call them as x1 and x2. Okay, similarly, if we have a cubic polynomial will have 3 roots. Okay, in the same way, if we have a fourth order polynomial, the fourth order polynomial will have 4 roots. If we have a fifth order polynomial, it will have 5 roots. And if we have the nth order polynomial, it will have n roots. So number of roots a linear or a non-linear equation possesses is certainly dependent upon the degree of the polynomial. If the degree of the polynomial is 2, it will have 2 roots. If the degree of the polynomial is 3, it will have 3 roots. And if the degree of the polynomial is n, it means it will have n roots. Fine. Now let's return to the fundamental equation that we have to solve. X cube minus x minus 4 equal to 0. Since the equation is cubic, okay, its order is 3. So we can say, or we say, sorry, the degree is 3. We can say that it will have 3 roots, x1, x2, and x3. Which method we'll be using to solve the given equation? Okay, we have an equation in hand and we have to find the roots of this equation. And we know the equation is nonlinear. The equation is cubic. Okay, and the question that in hand is finding the roots of this equation. Okay, there are many methods of solving this problem. The first and foremost method of solving nonlinear equation is, the first method that we'll be discussing is called the first method we will be discussing is called the bisection method. Let's start with the bisection method. It's called the bisection method. Bisection method. Bisection method, or it's also called the Bolzano method. or Bolzano method. So in today's lecture, we'll be starting with the bisection method or the Bolzano method. Bolzano's method. So how does this method work? Let's first of all understand the concept of bisection method. Okay. The concept of bisection method is if you have any nonlinear equation y as a function of x equal to 0, if you have any nonlinear equation y as a function of x is equal to 0, as we have previously, as is given to us, first and foremost, select two values of x. Take any two values of x. Select, take, or assume any two values of x. That is, assume any two values of x. Take any two values of x. We have to find the root of this equation. Okay, this is equal to 0. Y is a function of x is equal to 0. Take any two values of x. Take x1 and x2. Okay, find f of x1 and f of x2. That is, assume any two values of x. Since this is a polynomial in x, an equation in x, assume any two values of x. Take x1 and x2. Okay, substitute the value of x1 back in this equation. Okay, you will write x1 cube minus x1 minus 4 equal to something. Substitute the value of x2 in this equation, that's x2 cube minus x2 minus 4 will not be equal to 0 because x1 and x2 are not the roots. Okay, this equation will be equal to 0. This equation will be satisfied at those values of x which will be the roots of this equation. Okay, which will be the roots of this equation. But x1 and x2 are, we are assuming these two values. These are not the roots of this equation. Okay, so what we do, we have to assume two values, x1 and x2, obtain the value of f of x1 and obtain the value of f of x2. It's very important. F of x1 and f of x2 should have, it's very important condition, should have opposite signs. This is very important condition. Should have opposite signs. What does that mean? They should have opposite signs. That is, if f of x1 is, if you substitute the value of x1 in this equation, okay, if f of x1 is less than 0, then f of x2 should be greater than 0. Or if f of x1 is greater than 0, f of x2 should be less than 0. That is the signs of the equations x1 and x2. Okay, the signs of the equations f of x1 and f of x2 should be opposite. Okay, let me explain it graphically what we are right now doing. Let me draw an x-axis. Let's suppose we have an x-axis. Okay, and let's suppose this is our y-axis. Okay, so I will be calling this as my x-axis. Let's suppose this is our x-axis, and let's call this as y-axis. Okay, when we look at the graph of the nonlinear equation, the graph of the nonlinear equation can be any curve but not a straight line. Okay, let's suppose the graph of the equation y as a function of x, or this equation, is, say, for example, like this. Okay, let's suppose the graph of this function is as given. Let's suppose the graph of this y as a function of x is, this is our x-axis, let me extend it. Okay, let me suppose the graph of y as a function of x is here. The graph of y as a function of x is this curve. Okay, this is the graph of the function whose roots I have to find. Okay, see, the equation that we have, f of x is equal to 0. It means there is a particular value of x at which our entire function becomes equal to 0. That is this point. This is the point. This is the point at which our function f of x becomes equal to 0. Okay, so what I am doing is the equation whose roots I have to find is x cube minus x minus 4 equal to 0. Okay, so what does the Bolzano method say? We can say, in other words, first of all, plot the graph. Okay, so once we plot the graph of the given equation whose roots we have to find, we will be at least getting a point. Let me suppose this x-axis. So this is the point. This is the point at which the value of my function becomes equal, at which the value of the function becomes equal 0. Okay, so this is one of the root of my equation. This point is one of the root of my equation. Okay, in order to reach to this root, what I am doing, I'm selecting 2 points. I'm selecting one point here on the x-axis and calling this point as x1. Okay, and I'm selecting another point on the x-axis and calling this point as x2. Okay, and finding the value of the function at x is equal to x1. The value of the function is this much. Okay, let me extend this line. The value of the function at x is equal to x1 is f of x1. Okay, and at x is equal to x2, the value of the function is this much. Okay, this much. This is what I call as f of x2. Okay, what I am doing, the value of, if you look at f of x1, this is on the negative side of y, this is negative. And if you look at f of x2, this is on the upper side of, this is along the positive y-axis, this is positive. Okay, so f of x1 and f of x2 are the two values of the function at x1 and x2 which are opposite in sign. Okay, let me repeat whatever I have been doing. Let me repeat it. Repetition is, we are given a function y as a function of x is equal x cube minus x minus 4 equal to 0. X cube minus x minus 4 equal to 0. And we are asked to find the roots of this equation, to find the values of x at which this equation gets satisfied. So what the bisection or the Bolzano method says, first of all, in order to solve this problem with the help of bisection or Bolzano method, first of all, we are plotting the function. Okay, so once we went on to plot the function, we call, let's suppose the graph of this function, the graph of the given function is, say, for example, like this. Okay, let's suppose the graph of the function is like this. So this is the graph of a function y as a function of x. Okay, this is how the graph looks like. Now look at this point along the x-axis. This is the point at which our function f of x is equal to 0. Therefore, this value of x represents the point that is one of the solution of this equation. We have to find how much is the solution, how much is the value of this x. This is our question. Okay, so what does the bisection or the Bolzano method says? Bolzano method says, assume any two values of x. Assume x1 and assume x2. Assume any two values of x. This is your choice. Okay, obtain the value of x1, obtain the value of f of x1, find the value of this function at x is equal to x1. At x is equal to x1, find f of x1. At x is equal to x1, find f of x1. And at x is equal to x2, find f of x2. Okay, so at x is equal to x1, our f of x1 is having this value and it's negative. Fine, no problem. And x is equal to x2, our function is having this value from here to here. And if you look at this value, this is positive. Okay, we can say that this value is f of x2. This is the value of function at x is equal to x2. And this is the value of function at, this is the value of f of at x is equal to x1. Okay, Bolzano says that the values of f of x1 and f of x2 should be in opposite direction. Okay, if f of x1 is negative, f of x2 has to be positive. Okay, So once we are done with x1, once we have assumed we are guessing x1 and x2, obtaining f of x1 and obtaining x2, making sure that the sign of f of x1 and f of x2 is opposite, okay, then this is the solution, this is your solution, okay. So you have to move this x1 in this direction very, very close to this solution point, and you have to move this x2 very, very close to this solution point, okay. So we have to move x1 very close to the solution point, and we have to move this x2 very, very close to the solution point, okay. So how we will do it? The bisection method says the assumed values x1 and x2, the assumed values x1 and x2, now take the third value x3, which will be equal x1 plus x2 divided by 2. That's why this method is called bisection method, okay. So as far as the values of x1 and x2 are concerned, as far as the interval x1 to x2 are concerned, as far as the interval from x1 to x2 is concerned, this is the interval in which our solution is lying, okay. That's why this is called solution interval. This is called a solution interval, or this is also called the search interval. This is also called the search interval. You have to search your solution in this interval from x1 to x2. Now, so what we have done, once you have obtained the value of f of x1, f of x2, and you are making sure that f of x1 and f of x2 are in opposite direction. Now take the third value of x, that is x3, which will be x1 plus x2 divided by 2. Okay. Now let's suppose, now this x3 that we are obtaining, which is the average of two values x1 and x2, this x3 can either be here, okay, or this x3 can either be here. It means our x3, which is the average of these two numbers, can be here. This can be our x3, or our x3 can be here. Means I mean to say that our x3, the next assuming point, can be on the left hand side of our solution point. Let me call this solution point as x solution. This is x solution. Okay. So the next x3 will be either on the left hand side or on the right hand side of this x solution. Fine. Now, if x3 lies on the left hand side, if this is the case, okay, if this is the case, if this is the case where x3 lies on the left hand side of the solution, find the value of f of x3. Okay, substitute this x3 in your given action, in your given function. Okay, find the value of f of x3. Now if you look here, if this f of x3 is here, then the value of f of x3 is this much, and again it's negative. This is minus. Okay, the value of our function at x is equal to x3 is negative. So this is less than 0. Okay, then what you do, see, this is very, very important. If the value of this x3, once you substitute x3 in your given equation, when you substitute your x3 in the given function f of x, and if the substitution of x3 in f of x makes your f of x less than 0, then your new search interval will be x3 comma x2. This will be your new search interval. Okay, that is, now your solution lies between 2 points. Now your solution lies between 2 points. One is this point, another is this point, between x3 and x2. Okay, this is the case when f of x3 is less than 0. Otherwise, if your x3 lies on the right hand side of the solution point, if f of x3, when you substitute x3 back into your function, if f of x3 is greater than 0, if f of x3 is greater than 0, that is here. Okay, if f of x3 is greater than 0, that is, if your x3 lies here, okay, then your solution lies, where is the solution? The solution lies between x1 and x3. Then your search region becomes x1 and x3. This is very, very important. Okay, so let me repeat whatever I'm saying, because I believe that this is a concept that students should be familiar with to come up with the idea of the bisection method or the Bolzano's method. So what the bisection or the Bolzano method says, let me replot the graph. let's suppose the function that we have y as a function of x, I'm saying let its graph be like this. Okay, let's suppose this is the graph of our given function. Okay, this is the graph. So this is the point that we have to find. This is the solution point. I'm calling this as x solution. Okay, we are assuming 2 points on the we are assuming 2 points on the function of x. We are assuming x1 and x2. Okay, f x1 and x2, such that f of x1 and f of x2 are in the opposite direction. They have the opposite values. This is f of x2. They should have the opposite signs. Okay, so once we are sure that f of x1 and f of x2 have the opposite signs, so what we will be doing, we'll be taking the third value of x, that is x3, which is equal x1 plus x2 divided by 2, which is x3. Okay, now substitute the value of x3 in the equation f of x. Okay, you have f of x is equal to 0. This is the given equation. Okay, so now this x3 you have to substitute back in this equation. And if this f of x3 is less than 0, if f of x3 is less than 0, it means your x3 lies here. Your x3 lies here. So if you take f of x3, the value of the function at x is equal to x3, it will be this much, and this is negative. This is what the equation says. Okay, then your new search interval becomes, the new search interval is from x3 to x1, from x3 to x1, and we know this is correct because our solution is here. Okay, we have to take this x1 very very close to this x solution. So if our x3, if at x is equal to x3 the value of the function is negative, then we need not to take this x1, we need now to take the new search interval as x3 to x1. This is it. Okay, otherwise if the substitution of x3 back into f of x makes f of x3 greater than 0, it means then x3 does not lie on the left hand side of the solution. Okay, if this is the case, if the substitution of x is equal to x3, if the substitution of x is equal to x3 makes your equation greater than 0, that means x3 is here. Okay, because at x is equal to x3 our function is positive. Okay, x3 is here. Then our new search interval is, we need not to take this x1 sorry x2 now. Okay, our if our x3 is here, then our new search interval will be from x1 to x3. Our new search interval is x1 to x3. Okay, so we started with the search interval from x1 to x2. Now our new search interval can be from here to here or from here to here. Okay, so you see what's happening. Initially x1 was here, x2 is here. Okay, now based on these two conditions, either your x3 is on this side or your x3 is on this side. So is not your solution coming very very close to this x solution point? Okay, so what we will do now, we will take the average of these two values, that is x4 equal x1 plus x3 divided by 2. Obtain the value of now f of x4. Now if this f of x4 is less than 0, again then this x4 lies somewhere here, because at this value the function is negative. If at the value of x4, the value of f of x4 is greater than 0, then this x4 lies somewhere, this x4 lies somewhere, this x4 lies somewhere here. Okay, now you can take from here to here as your solution interval, or from here to here as your solution interval. So what is actually happening? From both the sides we are coming very very close to this solution. We are coming very very close to this solution point. So it means we started with a function. Okay, this was our x1, or let me clean it, let me draw it a bit wide. So this was our x1, this was our x2. We started with these two assumed values. We have to reach to this point, x solution. So what we are doing, we are taking average. Either x3 is here or x3 is here. Okay, if our x3 is here, then our solution interval is from here to here. Okay, fine. If our x3 is here, then our solution interval is from here to here. Okay, then we take the average again. Our x4 will be here or our x4 will be here. Okay, if x4 is here, then the solution interval is from here to here. If otherwise, then the solution interval is from this point to this point. See, every time what is happening, the gap between these x values is decreasing. This x value is moving towards the solution in this direction. This is moving towards left hand side towards, and finally we will reach to the point where our function f of x will be equal 0. Now, this is the theory behind it. Now let's approach our problem. The problem we had x cube minus x minus 4 equal to 0. We start with assume the two solutions, assume two values, assume the values of f of x, assume two values of x. Okay, we have to start with the two values of x. Let's start with the two values of x as we can take any two values. Okay, let's start with this is your choice. Okay, let's start with x1 equal, this is your complete choice. You can select any two numbers. X1 is equal to 1.5 and x2 is equal to 2.0. Okay, we are starting with two values of x. Fine. Now these are just assumptions. This is what we have assumed. Okay, this is a total assumption we are making. Fine. So now substitute the value of x1 back in this equation. This is your f of x. This is our f of x. So f of x1 will be equal 1.5 cube minus 1.5 minus 4, and that is equal, if we solve it, that comes out equal 1.5 at x is equal to 1.5. The value of the function is minus 2.125. Okay, minus 2.1.5, and find at x is equal to x2, the value of our function is f of 2. That becomes equal 2 cube minus 2 minus 4, and that is equal, at x is equal to 2, the value of the function becomes, that is equal to 2. Fine. So it means what we have done, we have assumed two values of x, x1 and x2. Okay, and we have obtained x1 at f of x1 is equal minus, f of x1 is equal to minus 2.125, and f of x2, that is equal to. So this is our first condition is satisfied. That is f of x1 is negative and f of x2 is positive. Fine. So we have obtained the two values at two assumed values of x1 and x2. We are obtaining the value of f of x1 and f of x2, and the two values are opposite in sign. Now what we find, we will take, these are the assumed values of f of x and f of x1. And we know when we take x1 is equal to this and x2 is equal 1.5, this we call as iteration 1. Iteration 1 means we are iterating it once. This is called iteration 1. Once we are done this much, once we have found the value of f of x1 and f of x2, we will do what we call as the iteration 2. We will do iteration second. Iteration second is, we'll find the value of x3, that is equal to x1 plus x2 divided by 2. That is equal, our x1 is 1.5, our x2 is 2 divided by 2. That's equal 1.5, 3.5 divided by 2, that is 1.75. Now we substitute this 1.75 back in the equation. F of that will be 1.75 cube, 1.75 cube minus 1.75 minus 4. Okay, and that comes out equal, that's equal minus 0.3906. Now it's here. Since f of x3 Since f of x3 is less than 0, therefore our new search interval will become 1.75 comma 2. This will be our new search interval. I think I will stop here now because the timing for the class is over. I will stop here now. From here onwards, how I am taking this, I will continue in the next class. Thank you very much.